installment of my graduate techniques presentations for this semester for remote sensing of rivers. My name's Ryan Richardson, and today we're going to be doing a little presentation on the introduction to unmanned aerial systems as platforms for remote sensing. So some of you may know me from on campus. My name's Ryan. I am a student in the Geography and Water Resources Interdisciplinary Masters of Science program. I work under Carl Legleiter as a graduate student, our fearless leader throughout the semester studying fluvial remote sensing. I have always really loved rivers, and this course has been a blast so far, and I'm really looking forward to all the other things we're learning about. Just to give you a little bit of background about who I am and what research I work on, I'm from the East Coast. I'm a transplant here to the University of Wyoming. Grew up in North Carolina, learned to kayak and fish there, and have taken those skills and my love of river all across this great country, and especially here out in the West. My research focuses on quantifying salmon spawning habitat in catchments in California. So in the bottom left, you can see there's me as hanging out as a river ranger in California for a while. Decided to come back to school and study those same rivers that I was protecting from my boat as a ranger. So if you have more questions about that, I definitely would love to talk and chat. There's a lot of really cool stuff that we've been applying to the rivers out in California. Some of the stuff that we're learning about in class with OBRA and depth retrieval methods, but also some really new stuff that we haven't covered yet in class, like structure for motion and grain size mapping. So more to come with that. I really got interested in UAVs while working with Toby Stegman, a fellow fluvial remote sensing lab mate of mine. We both got into the whole drone game and using drones to collect data about rivers. And so there's me on the bottom right teaching a class at Furman University, my undergrad. I went back for a little invited lecture series where I got to teach some students how to use drones and use drones safely for collection of structure for motion data. And yeah, ever since then, I've really been interested and hope that we can share some of that interest with you today. So let's go over some of the major objectives we're going to cover during this little mini series here. What are the different types of unmanned aerial systems? What are the different parts of a UAS? How do I plan a flight? And then also how to actually fly one of these things, as well as looking at some of the different research applications that we can actually use for remote sensing with a UAS. So the first thing is we got to just sort of figure out what are our different options for different types of UASs. Most of you probably think of the typical drone, quadcopter, which we'll cover here in the segment, but there's actually a whole host of different unmanned aerial systems that have been used traditionally, and some of the newer stuff that has been used for remote sensing even back in the very early stages of just collecting aerial photographs. So one of the first really basic systems that were developed were these balloons. So kind of like a hot air balloon, but in this case, this balloon's filled with helium. It has some rotors on either side, and it can carry a large payload. As you can see at the bottom, you have a pretty large camera being lifted up with this balloon system. Each one of these systems has its own strengths and weaknesses. Just like all the techniques we're learning about in this class with remote sensing, each one of these platforms has its own unique strengths and weaknesses. When it comes to the balloon, we got to think helium and hot air can only haul up so much weight, so your payload is really limited, as well as your ability to move this craft. Even though it has rotors on it, I would imagine with the Wyoming wind, we would see that thing getting blown all over the place. Another really basic rudimentary technique that was originally used to collect aerial photographs is the use of kites. Here in Wyoming, that would be great because the amount of weight that a kite can carry is dependent on how much wind you have to sustain the flight. So in the case of Laramie, I think we've got plenty of wind to go around, so we could probably haul up a pretty big camera system on one of these kites. Kite photography has been around since the early 1800s, and has been a really successful technique at collecting aerial images. However, just like the balloon, it's kind of hard to really get a large spatial extent with a single kite. So that's what's really cool about the new robotic options that we have with quadcopters and octocopters, is that we can actually carry a significant amount of stuff for a great distance with it. So one of the first things that kind of started off the robotic aerial system movement were helicopters, remotely controlled helicopters. Here's a pretty fancy one that you can't actually buy on the market, but this is a custom build that has a huge DSLR mounted to the front, and with a pretty sweet gimbal system. So a gimbal is a robotic piece of equipment that can actually stabilize a camera during flight. So that way we can collect really clear and sharp images, which are going to be crucial to collecting remote sensing data. Helicopters were popular in the beginning, but as we learned more about how to sustain flight and different options were developed, we realized that having more rotors on the actual UAS increases the stability and the payload for a given UAS. So in this case, we don't see too many helicopters out anymore, even though I think this one looks pretty sweet, and I definitely like those little foam foot pads they got on there. It looks like you could almost land this thing on the river if you wanted to. So the next one I want to talk about is the most common type of UAS that we're all pretty familiar with now in this day and age. It's just the quadcopter. Quadcopters have 4 rotors attached to this. This is a product from 3D Robotics you're looking at. It's the Iris. It's around $1,000. It comes with a gimbal system. You have to buy the GoPro separately, but it's a pretty cheap option to get started off in a UAS, and especially if you're trying to go apply this to some sort of research setting. These guys are great. They're really easy to use. Right out of the box, they are ready to fly. And that's what really has enticed and really made the drone game kind of explode over the past couple of years, is the fact that these things are so easy to use now, and they come out of the box just ready to get out and collect data. This is what I would definitely recommend for any of you guys that are going out and want to collect your own data. I think the Iris is a superior product, definitely to some of the other quadcopters that are on the market. The only thing though is it's pretty light, as you can see. It's which is great for flight times, and also for carrying more payloads. However, in the Wyoming wind, this can be a significant drawback, because the lighter the aircraft is, the more susceptible it is to getting thrown around by heavy winds, which, as we've already stated, definitely here in Laramie. So another option is to go with an octocopter, which is an 8-rotor system. This is a popular one produced by DJI, which is another popular drone business based out of Japan. This one in particular is way more expensive, and as you get more fancy systems that can carry larger payloads for longer times, you typically see an increase in price. So with this octocopter in particular, it ranges anywhere from $6,000 to $10,000, and that doesn't include the actual platform that you're trying to send up on it, whether that's a simple digital camera, or if you're trying to get really fancy and try to do some sort of multispectral sensor as well. But the great thing about an octocopter is with those eight rotors, you're able to maintain a really stable flight, as well as a significantly increased payload. One that's not often thought about, and I think that we really should be considering it for certain projects, is our fixed wing UASs. These are just standard planes that have been flying around from hobbyists for over 20, 30 years now. And what these actually have that a UAS like a quadcopter or an octocopter don't have is they can actually go for extended spatial extent. So I've seen online videos of these things traveling anywhere upwards of 20 to 30 kilometers. in a single flight, which is absolutely incredible and really not capable for an octocopter or a quadcopter given the current flight times that we see. But having said that, like everything, there is a significant drawback in that we can only carry very, very light payload. So the heaviest payload we could carry with a system like this would be a small GoPro, which may do the trick, but for a lot of the stuff that we use, the GoPros really aren't the best camera to be collecting remote sensing data. Another really great option, if you are trying to work in an area where a traditional UAS, like a quadcopter and octocopter, would be illegal, say if you have a project in a national park or within 5 miles of an airport where UASs are not allowed, you can get around that by using a non-motorized unmanned aerial system like this, which takes the benefits of a balloon and a kite and puts them together in this system called a helikite. So this is a helium balloon as well as a kite, and so it kind of takes the best of both worlds. The balloon helps increase the payload and stability of flight, and the kite itself in sustained winds can actually carry pretty significant payload. So you could actually haul up a DSLR with one of these systems for a sustained period of time. And like I said, the major benefit of this is getting around rules and regulations that restrict the access of quadcopters and octocopters, especially if you're working in wilderness or the national parks. Okay, so now that we've gone over some of the basic types of a UAS, let's talk a little bit more about the legal questions and the legal ramifications of using these systems. This is a hot topic issue. Everybody in the news is talking about it. But I kind of wanted to just give you a brief overview and also point you in the right directions for finding any information you might need with this. The proposed and current regulations that the FAA is currently operating under, the important things you need to remember is that you have to maintain a visual line of sight with the aircraft while you are flying it. So if you're operating one of these systems, you cannot get this thing out of your sight. And that includes if you have binoculars or some kind of assistance device. That doesn't count. It has to be the naked human eye. You have to be able to see your device. This is a pretty significant limitation for if you're trying to cover really large distances with these UASs. The other thing you got to remember is you can't operate within 5 miles of an airport, in a national park, in wilderness. These are all restricted flight areas. You can only fly during the day, even if you have lighted systems. So a lot of these systems have lights on board, but the FAA has regulated now that you are not allowed to fly outside of sunrise to sunset. So important restrictions to definitely keep in mind. Another thing you got to remember is that you can't go above 500 feet. So that's the flight deck for a lot of commercial aircrafts. And so you cannot operate a UAS within the airspace that is regulated for a commercial airspace unless you have an FAA exemption. So if you want to operate these things outside of the university in a commercial setting, currently you would have to have a commercial, or not a commercial, but a basic pilot's license as well as an FAA exemption. So there are a lot of rules and regulations, and it's constantly a pretty changing environment. I always want to point you guys to the link to the bottom there. That's the FAA rules and policies on UASs. And this is a good summary article that you could check out if you're interested in the latest and newest regulations that are currently out there. Okay, so let's take a look at some of the different parts of a typical robotic unmanned aerial system. So this is a great schematic that was produced by 3D Robotics, which is the company that our UAS here at the University of Wyoming is actually bought from. And I want to kind of walk you through some of the main components that you would expect to find on pretty much any UAS that's a quadcopter, octocopter setup. So hopefully I got my handy dandy laser pointer that can come in. There we go. So the main hub of where everything is connected is right here in the middle. This is the Pixox flight controller. So you can think about this, if you're familiar with how computers work, this is effectively the motherboard of the UAS. So everything is going to connect in, and it's going to be handled through this flight controller. You have a GPS unit right here that connects in. You have a receiver right here that talks to your remote control that connects in, as well as the battery, which is going to connect in over here. This guy up here is your ESC, which is your electronic speed controller. And so what the ESC does is it talks to the flight controller, and it figures up how much power to give to each one of these motors to accomplish the direction and the speed at which you are telling the UAV to travel in. So this guy right here is probably one of the more important pieces in the setup, because if this malfunctions, you're not going to be able to properly fly the aircraft. So over here, we also have a telemetry output, which this is talking to your ground control. So most UAVs nowadays come with, or you have to buy some sort of platform on the ground, whether it's a laptop or a tablet, that you're able to set up and have talking at a constant rate with the actual UAV while it's flying. Yeah, and like I said, you're also going to have gimbals and cameras that you can attach optionally, but all these features right here that you see are mandatory elements of pretty much any UAV that's currently on the market. Just wanted to point out, this is what we refer to as Cowboy 2. This is our UAS that we have at the Fluvial Remote Sensing Lab, and that we operate for our remote sensing projects. And this is a 3D robotics, kind of a quadcopter octocopter mix, in the fact that we have 2 motors on each of the arms. It's technically an octocopter, but it doesn't have that great stability of flight that a traditional octocopter would. So a kind of a mix of both worlds. We've had some issues with it. That GPS unit that's sticking up on top has had a malfunction. This is why we have Cowboy 2 and not Cowboy 1. Cowboy 1 had a significant catastrophic malfunction and crashed. It was no fault of our own. 3D Robotics happily replaced the entire drone for free because we were able to actually have those flight records recorded on our computer that showed that it was not our fault and that it was a malfunction within their own system. So something to think about. These things crash from humans and from sometimes they have a mind of their own. All right, so let's talk more about how to plan a flight. So where can we fly and where can't we fly? Well, obviously, I've already stated you can't fly within 5 miles of an airport. The FAA has also restricted flight in areas where there's buildings or a lot of a heavily populated area. You are not actually allowed to fly over people who are not a part of the UAS flight itself. So you can't fly over random people at all, which that seems to be broken pretty frequently with a lot of the videos we see online with these things. But technically you're not allowed to fly over it. So an area like Prexy's pasture would not be a great place to fly because it breaks those buildings and people's rules. The other thing you need to think of here in Wyoming is trees, especially if you're operating within a river environment. Oftentimes in the riparian, we have large trees that can actually get in the way of flights. And this might seem like, duh, Ryan, that trees get in the way of flights. But what you got to always think about is the wind. So we've had several flights that we've had to abort mid-mission because of the fact the wind was so strong that if we were not to abort the mission, we would actually be pushed into the trees, no matter how hard we were trying to fight the wind. When you can fly, you got to fly during the day. Like I said, watch out for the wind, and visibility is crucial because you have to maintain a visual line of sight. You can't have these things operating in the clouds or in a foggy environment. I know recently, or I guess about a year ago, one of these UASs landed on the White House's lawn. Hopefully none of you guys will take it to that extent. I think that guy was drunk anyway. So don't get drunk and fly UAS to the White House. It doesn't end well. I think he got let off, but probably a pretty big fine. So let's look at this thing that is called the Mission Planner. This is a open source piece of software that 3D Robotics released. So you can use this with any drone as long as you have the right capabilities to communicate with this software program. And so what you can see here is I've zoomed in on Laramie, And you can see there's a big red circle around the airport. This is the area where we are not allowed to fly, and it won't allow you to fly a UAS in that region because of the fact the airport's within 5 miles. But check it out right down here. This is the Laramie River, and it's right smack dab in the middle of this no-fly zone. So that's a great example of a river or an area in which we would really be interested in trying to do some flights in there, and we have actually tried. But we had to move our study sites further to the south to avoid that no-fly zone. During your flight, you can monitor different attributes of your flight: your altitude, ground speed, vertical speed, distance to your waypoints. All these. This is a great program, and I definitely recommend anybody who's getting into the game to definitely check it out. And we're going to actually take a few more closer looks at some of the features this program offers. So just like I said, don't fly drones in Prexy's pasture, but let's take a look and see how this program works and just give you a place where you know and you're familiar with and show you some of the capabilities of this program. So as you can see here, this is Prexy's pasture. I put in a bunch of waypoints, and you can actually plan out your flight before you go out in the field, which is the way you really should be doing it. It's the safest and most effective way to collect data in the field. And this is just a simple point and click system where you set up a grid and you say, okay, fly this circle. That's a really rudimentary way to do it, but there's actually really unique tools that are in the software that allow you to get a little bit more sophisticated. So say if I wanted to map out Prexy's pasture with a UAS with photos. And so I'm going to make a polygon of the area that I'm interested in with this that's noted with these red pin drops here. And then I'm going to tell the program over here, I'm going to fly at a certain altitude, and the angle of my camera is 235 degrees, as well as the field of view, which you're going to have to input manually in here, depending on what camera you have. And it will automatically plot a course, the most effective course for you to take during your UAS flight. So say if we change those parameters, what if it's a really windy day, which it is typically here in Wyoming, and we only can fly upwards of 15 meters. What you're going to see is the closer you are to the ground, the more flight lines you have to take because you don't have as much of the actual area you're looking at in the field of view. Okay, but we're really interested in rivers, right? This is remote sensing of rivers, not remote sensing of Prexy's pasture. So let's take a look at a river in North Carolina that we were looking at with the Furman group that I was giving that tutorial to. This is a polygon, again, I made of the river channel saying, hey, I want to map this river out. So let's look and see what we can do. Just like I did last time, drop those pins, made the polygon. And then I could actually put in those parameters over here, have some more realistic parameters, and then it actually comes up, even in a complicated polygon like a river, it can come up with the most effective flight path, and it'll tell you how long it'll take you to fly this. So in this case, I would have to realize that's not a realistic flight time because we only have about 10 minutes on our battery. So I would have to go back to the drawing board and try to break up this section into different chunks before I went out in the field. So what are some things, I know that we're going to talk about structure for motion in this class, and I just wanted to give you a brief intro into it. This is a slide that I borrowed from my collaborator, Toby Stegman, who did his his master's thesis on a restoration reach in Idaho on Teton Creek. And so this is some of his data and one of his slides that he's allowing me to use. So what we typically see here is the really great thing that you can use with a UAV is looking at ways to collect high resolution topographic data. That's really what a geomorphologist and river scientist were really interested in. How does the river change through time? Can we create these really high resolution DEMs? You can think of it like a similar data product to LiDAR, but it's a much, much higher resolution. So we're talking about having centimeter-based resolution compared to meter-based resolution when we're talking about LiDAR. So a really unique system. We're going to acquire the images with the UAV. The software packet that we use will find key points within each image that we collect and match them and align them to other photos that we're asking it to align to. And it's going to pump out a point cloud. That this actually over here is a high resolution dense point cloud. So these are individual topographic points that have retained their RGB values, and it outputs this beautiful data product. But if we're going to use it as geographers, we're going to need to bring it into some sort of spatial reference system. So having these ground control targets set up, in our case, they're little orange CDs that we're going to actually survey in during the flight, is really helpful for creating a model that you can bring into a coordinate system. So this is just a brief introduction. We'll definitely talk more in this course about structure for motion, and I'm really excited about sharing some of this knowledge that we've developed here at the University of Wyoming. So, like I said, here's some of the basic research applications. Structure for motion can create high-resolution topographic products. It can be used for geomorphic change detection, which we're going to talk about, morphological sediment budgeting, hydraulic modeling, grain size mapping, which is coming up in my next presentation, and as well as depth retrieval. Sometimes we can get in really shallow, very, very clear water, we can get depth measurements in the water column from structure for motion. But a lot of this is still preliminary work and is being really pioneered by James Dietrich as well as our colleagues at the University of Oregon. So if you're interested, that's definitely where you should check it out. The other thing that we can create with these is simple ortho photos, which can help with not only geomorphologists, but ecologists and wetland scientists that are looking at trying to classify habitat as well as wetland delineation. So with that, I know there was a lot. Hopefully, if you have any questions, you can email me at the email there, or also comment in the links below. I don't really know how this thing's going to be set up, but hopefully there'll be a way for you to comment and ask questions if you have any. But I want to also direct you to our lab group's website at fluvialremotesensing.org, where you can see all the latest and greatest that we're working on here at the University of Wyoming. And as the president of this of our laboratory, I definitely want to say that we have a lot of stuff really that's coming online and really exciting stuff. So take a look, check it out. I hope you enjoyed the talk and look forward to your questions.